Did you know that right within our solar system exists a planet so harsh it could burn away any thought of life? Extreme temperatures, intense radiation, and relentless meteor showers have turned it into a world almost impossible to set foot on. Yet, it is precisely this harshness that makes Mercury one of the most fascinating mysteries to be unraveled. In this video, we will explore layer by layer the secrets of the planet closest to the Sun. And trust me, you will be surprised by what science has discovered. Hit subscribe and stay until the end of the video so you don't miss any detail. When it comes to the journey of conquering Mercury, we often immediately think of the harsh challenges of a world just over 57 million kilometers from the Sun. No atmosphere, temperatures that can swing from nearly 430 degrees Celsius in the daytime down to 180 degrees Celsius at night, and relentless solar radiation that erodes any device daring to get close. Yet, overcoming all these challenges, humanity still decided to bet on an almost unbelievable long journey, the Bepi-Colombo mission. This is not just a spacecraft, but also a testament to the power of international cooperation and the thirst to understand the ultimate mysteries of the solar system. Imagine this. To reach Mercury, Bepi-Colombo cannot simply fly straight like an arrow. The sun's gravity is so strong that if it were launched directly, the spacecraft would be pulled into a spiraling orbit and plunge straight into that giant star. Instead, engineers had to calculate a complex trajectory, like an intricate dance among planets. Over 7 years, the spacecraft must perform a series of gravity assists, flying past Earth, Venus, and Mercury itself multiple times to gradually slow down. Only this way can it be gentle enough to decelerate and fall into Mercury's embrace instead of being swallowed by the sun. What makes this journey particularly fascinating is its scale. In total, Bepi-Colombo will travel more than 8.5 billion kilometers, a distance many times greater than that between Earth and Pluto. All this just to reach a tiny planet, even smaller than Jupiter's moon, Ganymede. But it is precisely this modest size and dangerous position that turns Mercury into an ideal natural laboratory, a place where we can directly observe the processes that shaped all rocky planets, including Earth. To fully understand Bepi-Colombo's value, we need to look back at the past. Before it, only two missions had ever approached Mercury. NASA's Mariner 10 in the 1970s was the first spacecraft to fly past the planet, but it captured only about 45% of the surface. It wasn't until Messenger, launched in 2004 and entering orbit in 2011, that we had our first global view of the innermost planet. Messenger brought a host of shocking discoveries, from the unexpected presence of water ice in permanently shadowed polar craters to evidence that Mercury had undergone massive volcanic eruptions. But Messenger's orbit leaned toward the South Pole, leaving data on the southern hemisphere limited, and that very gap paved the way for Bepi-Colombo. The highlight of Bepi-Colombo lies in its unique structure. Instead of just one orbiter, it is a dual system consisting of two scientific satellites carried by an interplanetary propulsion module. When it arrives, the two satellites will separate and fly into different orbits around Mercury, giving us for the first time a simultaneous view of the planet's magnetic field, surface, and interior. The Mercury Planetary Orbiter, MPO, developed by the European Space Agency, will focus on the surface and geological structure with high-resolution cameras and spectrometers capable of analyzing mineral composition. Meanwhile, the MIO satellite, developed by Japan, will concentrate on Mercury's weak and mysterious magnetosphere, a phenomenon that has challenged scientists for decades, as no one clearly understands why such a small planet can sustain a magnetic field. The name Mio is not only scientific but also carries cultural meaning. In Japanese, it means waterway, evoking the routes once crossed by ancient explorers. For Bepi-Colombo, Mio symbolizes the long, challenging journey that also opens up uncharted lands of knowledge. And Bepi-Colombo, the mission's overall name, honors Italian mathematician and engineer Giuseppe Bepi Colombo, who proposed the use of planetary gravity to navigate spacecraft, an idea that has now become the foundation of countless interplanetary missions. Right from its first flybys, Bepi-Colombo has proven its worth. In October 2021, when it skimmed past Mercury at an altitude of about 200 kilometers, it sent back stunning close-up images that revealed ancient craters. Among them, particularly striking was the Caloris Basin, one of the largest impact craters in the entire solar system, spanning 1,550 kilometers. These observations are not just beautiful images, they help scientists retrace the planet's formation history, from violent impacts to the gradual cooling and contraction of its crust. Beyond images, Bepi Colombo has also brought an entirely new dimension: the sounds of space. Thanks to accelerometers and magnetometers, raw data was translated into frequencies humans can hear. The result, for the first time, we could hear the spacecraft's flyby of Mercury, the oscillations of its magnetic field, and even the changes in solar radiation pressure. These sounds are not only unique, but also help the public better feel the harshness and vibrancy of a seemingly distant world. All these details are only the beginning. Bepi Colombo is still on its way to its historic rendezvous in December 2025. But even now, it has already shown us that the journey is just as important as the destination. Every flyby, every piece of data collected adds a fragment to the complete picture of Mercury, a small planet that holds the key to big questions. Why do some planets maintain magnetic fields while others don't? What caused Mercury to shrink, leaving behind giant cliffs on its surface? And most importantly, how can what we learn there shed light on Earth's own ancient history? While most of us imagine Mercury as nothing more than a scorched, barren, and desolate rock near the sun, in reality, a spectacular mystery is unfolding around it, a mystery only discovered in the past few decades. It is the gigantic sodium tail stretching millions of kilometers behind the planet. This discovery stunned many scientists because until then we were only familiar with seeing such long, dramatic tails on comets, not on a rocky planet. And yet, Mercury, the smallest and innermost planet, is behaving like a disguised comet right within our planetary system. The story began in the mid 1980s when astronomers first detected the emission light of sodium atoms in Mercury's extremely thin outer layer. At that time, it was thought to be just an interesting component of the planet's fragile atmosphere. In fact, the exosphere, a sparse layer of particles ejected from the surface. But in the early 21st century, a team at the McDonald Observatory in Texas used a specialized filter for sodium light, and what they saw went far beyond all expectations: a faint streak stretching millions of kilometers behind Mercury. At first, they suspected their own instruments, but after verification, there was no denying it. Mercury truly had a massive tail. What created this strange tail? The answer lies in the fierce interaction between Mercury's surface and the sun. Without a thick atmosphere like Earth's for protection, Mercury's surface is constantly bombarded by ultraviolet radiation, solar wind, and high-energy particles. This process releases sodium atoms from the planet's crust, throwing them into space. Once ejected, the sodium atoms are swept away by the solar wind, trailing into a long streak like a comet's glowing tail. The only difference is that instead of ice turning into gas, here it is metallic elements stripped from the surface. As scientists began to monitor this phenomenon more closely, they discovered that Mercury's sodium tail is not always the same. Its length, brightness, and shape change cyclically, depending both on Mercury's orbital position and the sun's activity. Particularly during strong solar flares, the solar wind can make this tail blaze brightly, stretching up to 2.5 million kilometers, nearly the distance from Earth to the moon, multiplied by 6. This is a perfect example of how the sun is not just a warm light in the sky, but an energy engine capable of shaping the very appearance of planets. Space missions, from Messenger in the past to Bepi Colombo today, have all contributed to confirming and expanding our understanding of this phenomenon. Messenger once measured the unusual distribution of sodium, potassium, and calcium in the exosphere, showing that each element has its own behavior. While sodium concentrates into the long tail, potassium is distributed clearly at the poles, while calcium appears more in the nighttime equatorial region. This very diversity has sparked a series of questions. By what different mechanisms is Mercury's surface being eroded? Is it due to small meteorite impacts or simply evaporation under solar radiation? And most importantly, what can these atomic traces reveal about the planet's primordial chemical composition? This is where Bepi Colombo becomes the decisive factor. With its modern instruments, especially the ultraviolet spectrometer FIBAs, the spacecraft can precisely measure the light emissions of each type of atom in the exosphere. This not only helps identify the composition, but also tracks how they change over time by day night cycles, by orbital position, and especially during solar storms. Instead of just a few images or short term measurements, humanity may now have a long term systematic dataset to, for the first time, draw the complete picture of Mercury's ghostly tail. And this tail is not just a beautiful phenomenon, it is a window into the planet's past. By studying the composition of the escaping atoms, scientists can infer which types of rocks are being eroded and even deduce the distribution of minerals beneath the surface. It is like reading an ancient diary that Mercury unintentionally wrote, each page torn and scattered into space by the solar wind. Beyond that, Mercury's sodium tail also has a broader meaning. It helps us understand how planets interact with their parent stars. Among the hundreds of planetary systems discovered around distant stars, many planets lie close to their stars under conditions even harsher than Mercury's. By observing this familiar world, we can extrapolate to understand how exomercuries are evolving. Do they also have atomic tails stretching millions of kilometers? And if so, what would that reveal about their surface erosion and magnetic activity? The truth is, even with all our modern technology, we have only just touched the outer layer of this mystery. Each time Bepikai Colombo flies by, it adds another piece to the puzzle, from crater images to data on magnetic fields in the exosphere. But the sodium tail, that ghostly light stretching into the darkness, remains one of the most captivating questions because it directly links the surface, the fragile atmosphere, and the fierce solar wind. It is fascinating to think that while we often dismiss Mercury as a boring planet, too small, too hot, too close to the sun to be of any interest, it actually hides a phenomenon so spectacular that it can be seen from Earth with specialized telescopes. And it is precisely this kind of surprise that makes science come alive. There is always something strange hidden in the most unexpected places. When we think about strange astronomical phenomena, the name Mercury rarely comes to mind first, but this tiny planet is delivering a surprise powerful enough to change the way we see planets near the sun. Mercury's gigantic sodium tail is not just a rare feature, but also a natural laboratory that helps scientists test the fundamental principles of the universe right before our eyes. And what makes it even more fascinating is the combination of many factors, from solar wind, micrometeorite impacts, to the subtlety of light radiation pressure. Let's start from the root: Mercury's position. Closer to the sun than any other planet, Mercury must endure intense radiation and fierce solar wind. Every second, trillions upon trillions of charged particles from the sun bombard its bare surface. Without a thick atmosphere like Earth's to shield it, Mercury becomes a direct victim of this constant particle storm. The result is a process called surface sputtering, where atoms are knocked out of the rocks and minerals. And among them, sodium, relatively abundant in the crust, is the easiest candidate to be released. This is where we see the beauty hidden within the harshness. When sodium atoms are ejected, they don't simply float aimlessly around the planet. Instead, they immediately feel the effect of the sun's light radiation pressure. Each photon of sunlight hitting a sodium atom acts like an invisible hand pushing it away. The pushes are extremely tiny, but happening continuously and simultaneously across millions of atoms, they stretch into a colossal structure, the sodium tail spanning millions of kilometers behind Mercury, and as an unchanging rule, it always points away from the sun. However, the story doesn't end there. Mercury's sodium tail is not only created by light radiation, but is also influenced by the tiny bullets of the cosmos, micrometeorites. Without an atmosphere to slow them down, even the smallest cosmic dust particles can strike Mercury at tremendous speeds. Upon impact, the released energy is enough to vaporize part of the surface material, once again liberating sodium. These seemingly invisible impacts play a quiet but important role in sustaining the sodium tail. So, how can scientists see a phenomenon invisible to the naked eye? The answer lies in the characteristic wavelength of sodium light, 589 nanometers. This is the very wavelength once used in classic sodium street lamps. When sodium emits this light, it becomes a special signal that can be filtered and amplified using telescopes equipped with specialized filters. Thanks to this technology, astronomers on Earth can detect and even measure the variations of the sodium tail over time. And even more interesting, Mercury's sodium tail is not static. It changes dramatically according to the planet's 88-day orbital cycle. Surprisingly, the tail does not reach its maximum at perihelion, when Mercury is closest to the Sun, but 16 days afterward. The reason lies in the Doppler effect. When Mercury moves away from the Sun at its highest velocity after perihelion, the sunlight is redshifted. This shifts the sodium absorption lines in the solar spectrum outward, allowing sodium in Mercury's atmosphere to absorb and reflect light more effectively, making the tail shine brighter. It is a perfect example of how light physics and planetary motion intertwine to create a unique astronomical phenomenon. This sodium tail also provides scientists with a natural investigative tool. By observing its brightness and shape, researchers can deduce the strength of the solar wind, the rate of micrometeorite impacts, and even the chemical composition of Mercury's surface. In other words, each time Mercury sweeps its sodium tail through space, it is like sending us a detailed report about the condition of the planet and its surrounding environment. Notably, the existence of this tail also changes how we classify celestial objects in the solar system. In the past, tails were almost an exclusive feature of comets, icy bodies blazing through the planetary system. But Mercury, a rocky planet, possesses a massive sodium tail. This breaks the traditional mold, forcing us to expand the definition of tailed objects. It turns out that even a planet can carry a feature once thought to be exclusive to comets. Mercury's sodium tail is not just a beautiful phenomenon, but also a window into the history and evolution of this planet. Through it, we better understand how radiation, impacts, and gravity act on a planet in a harsh environment. And most importantly, it reminds us that even the smallest and seemingly quiet worlds hide unexpected secrets, ready to astonish anyone willing to look closer. If Mercury's sodium tail amazes scientists with its unexpected beauty, it is the careful observations that have revealed deeper secrets about how such a small planet interacts with its central star. What truly excites researchers is not only the enormous scale of that orange-yellow luminous tail, but the fact that it changes according to a complex cosmic rhythm, where orbit, solar wind, and wandering dust particles all take part. The first glimpse of the sodium tail came from accidental observations. At the McDonald Observatory, astronomers discovered traces of this faint light almost unintentionally while they were focused on another spectroscopic experiment. Ironically, the great moments in science often do not arise from detailed planning, but from stumbling upon an unforeseen phenomenon. From that chance discovery, the scientific community began to open an entirely new chapter in the study of Mercury. To see that faint tail more clearly, scientists had to use a coronagraph, a tool designed to block out the sun's blinding light, allowing them to detect faint streaks around a tiny planet. In that astronomical scene, Mercury's sodium tail appeared like a golden ribbon quietly streaming into the dark void of space. It was not always easy to spot, and each successful detection was the result of months of planning, waiting for the right position and the right moment. But the reward for such patience was a rare cosmic dance, where the tail stretches and dims in sync with the rhythm of orbital mechanics. This phenomenon immediately raised larger questions. If a rocky planet like Mercury can release sodium and extend it into a tail millions of kilometers long, what would happen to other planets under even harsher conditions? Scientists quickly realized that studying this phenomenon not only helps us understand Mercury, but can also shed light on the entire solar system and even beyond. First of all, it provides a window into planetary evolution. Every sodium atom escaping from Mercury's surface is like a memory particle sent into space. Over billions of years, this slow loss could alter the planet's surface composition, depleting the more easily released elements. At today's rate, humans will never notice a clear change within a single lifetime. But on astronomical timescales, this could be one of the mechanisms shaping the final appearance of the planet. From that perspective, Mercury becomes a reference model for thinking about distant planets. In other star systems, where hot Jupiters, giant planets orbiting very close to their parent stars, exist, radiation and stellar winds are far more intense. If a small world like Mercury can produce a 5 million kilometer long tail, then those giants can certainly release massive amounts of material, creating tails even more spectacular. Thus, observing Mercury's tail has opened up a new method for detecting and analyzing exoplanets. Astronomers are now applying similar spectroscopic techniques to search for faint traces around distant stars. When starlight passes through matter escaping from a planet, it leaves characteristic lines in the spectrum, like a chemical signature. Detecting those signatures means not only confirming the presence of a planet, but also inferring its composition, temperature, and even its mass loss. In other words, Mercury has become a bridge from observing planets in the solar system to exploring worlds far away. Moreover, the sodium tail phenomenon helps scientists better understand the interaction between airless planets and the solar wind. In fact, a similar sodium tail has been detected around our own moon. This shows that it may be a widespread phenomenon occurring on any bare celestial body directly exposed to energetic particles from its central star. Thus, instead of seeing it as a rare curiosity, scientists now regard sodium tails as a natural feature included in the dictionary of cosmic processes. And to take this understanding to the next level, we cannot overlook space missions. After Messenger, Europe and Japan have now collaborated on the Bepi-Colombo project, a probe that will officially enter Mercury's orbit at the end of 2025. Equipped with advanced instruments, it will deliver unprecedentedly detailed data, especially about the exosphere and sodium tail. Scientists hope to map the three-dimensional dynamics of the tail, tracking its variations by day, by orbit, and by solar wind cycle. These data will not only answer the question, why does Mercury have a tail, but also help predict how other planets might respond in the harsh environments around their stars. What is fascinating is that, from a chance discovery in Texas, the story has spread across the universe. It connects the planet closest to the sun with distant worlds we can only see through telescopes. It links atomic physics, orbital mechanics, and cosmic aerodynamics. And above all, it reminds us of a truth: the universe never stops surprising humanity. Mercury, once thought to be dull and of little research value, turns out to hold one of the most important clues to understanding planetary systems and their evolution. In every faint glow of its sodium tail, perhaps there lies a message that countless secrets are still waiting to be uncovered if only we continue to look up at the sky and never stop searching. If there is any planet in the solar system tough enough to challenge the resilience of human intellect, it is Mercury. It may sound paradoxical, a planet much closer to Earth than Jupiter, Saturn, or even Neptune, and yet for decades it was almost forgotten. Not because we weren't curious, but because reaching Mercury is a task so difficult it seems almost absurd. The problem lies in its orbit and position. Mercury orbits the Sun in less than 88 Earth days, making it the fastest orbiting planet. When a probe from Earth approaches, it must not only fight against the Sun's immense gravity, but also decelerate at just the right moment to avoid slingshotting past, like a pebble flicked from a slingshot. This is the troublesome paradox. The closer you send a spacecraft toward the Sun, the more gravity pulls it into an even faster plunge, which means an enormous amount of fuel is needed to slow it down. But fuel itself makes the spacecraft heavier, increasing launch costs and limiting how much scientific equipment it can carry. That is why, after Mariner 10's flybys in the 1970s, Mercury had to wait nearly 30 more years before humanity could return. And that return bore the name Messenger, a masterpiece of intellect and creativity. Messenger's plan resembled a colossal detour, lasting more than 6.5 years and covering nearly 8 billion kilometers. Instead of heading straight for Mercury, it flew past Earth, twice past Venus, and 3 times skimmed Mercury itself before slowing down enough to be captured by its orbit. This was the art of using gravity assists, a technique orbital mechanics experts describe as using the pull of other planets to naturally redirect and slow down a spacecraft. If spaceflight were like mountain climbing, Messenger had found the winding path around the slope, longer but manageable, instead of attempting a vertical cliff face. Even upon arrival, the challenges didn't end. Mercury is a world of extreme contrast between light and darkness. By day, temperatures soar above 430 degrees Celsius, hot enough to melt lead. By night, they plunged to minus 180 degrees Celsius, colder than Antarctica. Placing a spacecraft in such an environment is like testing a metal block by putting it into a furnace and then plunging it into ice. To survive, Messenger was equipped with a special ceramic heat shield, always facing the sun like a giant shield. Its solar panels were designed to tilt away, avoiding absorbing so much energy that they would burn themselves. And to optimize further, engineers even used solar radiation pressure like a light sail, helping the spacecraft adjust its speed without consuming much additional fuel. When it officially entered Mercury's orbit in 2011, Messenger opened an entirely new era. In just a few years, it captured over 200,000 images, mapping almost the entire surface of the planet, an achievement we'd never had before. And those images revealed a world full of surprises. We discovered that Mercury's surface is not just dull gray plains of rock. It is etched with massive craters, collapsed mountain ranges, and vast valleys, evidence of a planet that once shrank as its giant iron core cooled. Messenger also found traces of volatile elements such as sulfur and potassium, substances scientists had once thought could not exist under such scorching conditions. Most striking of all was the discovery of signs of water ice in polar craters, places the sun's rays never reach. On a world hot enough to melt metal in daylight, the idea of ice is almost paradoxical. Yet that is where science is beautiful. Paradoxes open new doors for us to understand the universe. And not just the surface, Messenger also helped decode Mercury's heart. The planet's weak but surprising magnetic field suggests it still has a massive liquid iron core, proof that this small planet remains dynamic, not just a cold, dead rock. This raises the question, why has a small, old planet like Mercury kept part of its core molten, while many other planets cooled long ago? Messenger's journey was not just an exploration of one world, but a reminder of human audacity. We dared to bet on a detour idea, on technologies that seemed fragile and reaped results beyond expectations. Finally, when its fuel ran out in 2015, Messenger plunged into Mercury's surface, leaving a permanent scar as proof of humanity's drive to explore. Today, the data it left behind is still being analyzed, revealing new surprises. And soon, this small but harsh planet will once again be visited by Bepi Colombo, a joint mission between Europe and Japan. This time, we expect to go even deeper, not just mapping, but studying the details of Mercury's core, magnetic field, and even the possibility of special conditions never before imagined. With each step forward, Mercury has gone from a forgotten planet to a gateway into the secrets of the solar system's formation and evolution. And most importantly, it reminds us, in this universe, nothing is truly boring. Every world, no matter how harsh, has a story worth listening to, if we are patient enough and brave enough to uncover it to the end. On April 30th, 2015, Messenger ended its journey with a violent crash onto Mercury's surface. For many, this was a tragic end for a spacecraft that had carried so much hope. But in reality, it was a farewell full of glory. After more than a decade roaming across 7.9 billion kilometers, Messenger not only left its mark on the surface of a small planet, but also etched its name deeply into the history of space science. What made Messenger special was not just the distance it traveled, but also the treasure trove of knowledge it brought back. Among its most important discoveries, perhaps none was more surprising than Mercury's weak yet persistent magnetic field. Earth maintains its magnetic field thanks to an outer iron nickel core that is hot and constantly in motion, a natural dynamo. But Mercury is different. It has no moon to stir its core the way the moon affects Earth, nor does it spin quickly. Yet its core still remains liquid, still generating a magnetic field, albeit only 1% as strong as Earth's. Scientists gradually realized that the main culprit was Mercury's eccentric orbit, the largest in the entire solar system. When it approaches the sun, gravity tightens its grip on the planet. When it moves away, that force relaxes. This constant expansion and contraction, like a colossal heartbeat, kept Mercury's core from ever sleeping, generating enough friction to keep the liquid iron in motion. In other words, it was Mercury's wobbling orbit that kept its heart alive. Thanks to this magnetic field, Messenger observed an extremely fascinating phenomenon: Mercury's magnetosphere, the fragile protective layer against the solar wind. Being closer to the sun, Mercury endures solar wind pressures tens of times stronger than Earth. The thin magnetosphere is compressed right down to the surface, turning it into a chaotic battlefield. Here, magnetic reconnection events occur hundreds of times more often than on Earth. Each time magnetic field lines clash and snap, enormous energy is released, hurling charged electrons into space and creating explosive bursts of energy that MESSENGER recorded thousands of times. Strangely, most of these events were concentrated in the northern hemisphere, making it a particularly unstable and violent sky. Not stopping at the magnetic field, MESSENGER also allowed us to hear Mercury's whispers through its spectrometers. Spectral data revealed a shocking truth. Mercury is richer in volatiles than any other rocky planet. Potassium, sodium, sulfur, magnesium, and even chlorine coat the surface, completely contradicting the long-held belief that volatiles near the sun would be entirely burned away. This discovery forced scientists to reconsider the model of solar system formation. If a planet so close to the fire, like Mercury, still retained such a large amount of volatiles, then clearly something in the early history of the solar system happened differently from what we imagined. Mercury is not just a gray rock, it is a primordial diary, preserving secrets of the solar system's earliest days. And the secrets did not stop there. Mercury's thin atmosphere, more accurately called an exosphere, brought incredible surprises. MESSENGER discovered that it is filled with volatile elements escaping from the surface, blown away by the solar wind into a tail trailing behind the planet, making Mercury sometimes look like a pale golden comet. Calcium glows brightly at dawn, sodium forms a faint luminous streak, magnesium streams out from the night side. Even water vapor appears, possibly from comet impacts or from hidden ice pockets deep in permanently shadowed craters. MESSENGER confirmed a once controversial hypothesis. Water ice exists on Mercury. At its poles, in craters that never see sunlight, radar from Earth and imaging data from MESSENGER revealed massive deposits of ice, estimated to be in the trillions of tons. For humanity, this is not only a scientific discovery, but also a far-off prospect. One day, this ice could become a resource for human outposts. Back on the surface, MESSENGER painted a far more complex picture than we ever imagined. It found traces of ancient volcanoes, lava flows that once poured across the planet, evidence that Mercury was once geologically active and not dead on arrival. Giant impact craters, mysterious hollows possibly created by volatile sublimation, and most notably, clear evidence that the planet is shrinking. MESSENGER showed that Mercury's diameter has decreased by more than 14 kilometers since its formation, a figure far greater than predicted, proving that the planet is still evolving. All of this transformed Mercury from a world once dismissed as boring into a magnificent natural laboratory. It preserves primordial secrets while still undergoing geological processes today. MESSENGER not only opened our eyes, but also forced us to rethink questions we thought were already answered. How did the solar system form? Why does a small planet still maintain a hot core? And could this scorching world one day become a stopover for humans? In retrospect, MESSENGER's achievements shine even brighter because of the silence of its departure. It did not have a noisy death, nor did millions watch its final moments like other famous missions. Yet within the scientific community, its legacy is irreplaceable. And now we await the next mission, Bepi Colombo, expected to arrive at Mercury in 2025. If MESSENGER was the pathfinder, then Bepi Colombo will be the successor, bringing answers to the questions MESSENGER raised. If there is one thing that makes scientists both fascinated and puzzled when looking at Mercury's surface, it is the blend of ancient traces and unexpectedly youthful structures. Every crater, every crack, every light and dark streak is like a diary page left behind by this planet from the dawn of the solar system. Let's begin with the unique colors recorded by the MESSENGER spacecraft. Unlike the monotonous gray of the moon, Mercury is adorned with pale cream and light beige patches interspersed with darker gray streaks. The darker regions, according to spectral analysis, may contain high amounts of graphite, the same material we use in pencils. This has led scientists to ask, was Mercury's primordial crust richer in carbon than we thought? And why has it retained that composition after billions of years of being scorched by the sun? Not only that, the brighter regions reveal something different. Some of them are associated with structures called hollows, mysterious cavities found only on Mercury. When Messenger first sent back images, scientists initially thought they were the result of impacts, but closer analysis showed they did not match any crater models. These hollows have gently sloping, sharp edged walls, and most notably, still gleam as if they are very young. They appear to have been formed when volatile substances within the ground evaporated and vanished, leaving voids above that collapsed. If that is true, then Mercury is not a completely dead world, but one where geological processes are still quietly at work even today. In addition to the hollows, massive cliffs known as lobate scarps are vivid evidence that this planet is shrinking. As the metallic core gradually cools, the outer crust contracts, compressing and thrusting upward to form natural walls hundreds of kilometers long. Some cliffs rise thousands of meters high, slicing across craters, lava plains, and everything else in their path. That is why scientists believe Mercury's diameter has shrunk by more than 14 kilometers since its formation. A figure that seems small, but on a planetary scale, it is enough to rewrite the entire surface landscape. More importantly, it shows that this planet is younger than we thought, still moving in its own way. But it is not only internal processes. Mercury's surface also preserves traces of catastrophic impacts. Overlapping craters of different ages tell the story of a world battered by a cosmic hailstorm since the dawn of the solar system. Among them is the Caloris Basin, one of the largest scars in the solar system, spanning over 1,500 kilometers. The impact that created it was so powerful that shockwaves traveled across the entire planet, deforming even the terrain on the opposite side. Today, that deformed region is called tangled terrain, a chaotic landscape where peaks and fractures crisscross as if the surface had been kneaded from within. This single scar alone is enough to remind us that Mercury once endured events powerful enough to shape an entire planet. Despite its harshness, Mercury also holds some gentler surprises. Water ice at its poles, for instance. Deep inside craters that never see sunlight, this ice has persisted, reflecting radar from Earth and later confirmed by Messenger. Ironically, the planet closest to the Sun contains a significant amount of frozen water. Though incomparable to Earth, that mass of ice still opens up the prospect of a potential resource should humanity one day set foot there. It was also thanks to Messenger that we learned about Mercury's tenuous outer layer, the exosphere. Unlike a true atmosphere, this layer is too thin for gas particles to collide with one another. But that does not make it any less fascinating. Elements such as sodium, potassium, magnesium, even calcium, and water vapor have been detected there. Some come from the surface, evaporating under heat and radiation, while others are swept in by the solar wind. When sodium particles stream out behind, they form a long tail like a comet's, making Mercury the only planet in the solar system with such a strange hybrid appearance, both a planet and comet-like. If a lucky observer were to stand on Mercury and look up at the sky, they might see a faint golden glow like city lights reflecting in the night. What intrigues scientists most is why Mercury's magnetic field is so weak, only about 1% of Earth's, yet still strong enough to provide the planet some protection from the solar wind. Its eccentric orbit subjects it to uneven tidal forces, perhaps keeping its core still molten, driving a hidden dynamo that sustains the magnetic field. And because its magnetosphere is compressed right down to the surface, magnetic reconnection processes occur frequently, sending electrons shooting out with hundreds of thousands of electron volts. Messenger recorded thousands of such events, opening a new window of research into magnetic interactions in the extreme environment near the Sun. All these details, from the shrinking cliffs, the youthful hollows, giant impact craters, frozen ice, to the comet-like tail, paint a picture of Mercury full of contradictions, yet endlessly captivating. A planet that is both a vivid testament to the solar system's chaotic past and a gateway to unanswered questions. And that is precisely why, when looking at a single image of Mercury, we see not only a scorched world, but also history, movement, and secrets yet to be uncovered.